The universe is alive and forever recycles and gives birth to planets, galaxies, and stars. Giant stars, incredibly vast in size, explode, giving birth to hundreds, even thousands of infant stars, which come to be ringed with living planets, many just like our own. And this is how our own story begins. Our ancient ancestors journeyed here from the stars. Life gives birth to life, and stars give birth to stars in an endless cycle of death and rebirth. It is a cosmic dance which has been ongoing for all eternity. Some stars give birth as they die, exploding in a vast supernova and spawning hundreds of baby stars. Examples of these cosmic reproductive cycles of death and rebirth are all around us. The ancient star of Orion grew old and exploded in a vast supernova millions of years ago, becoming the largest star factory in the heavens. Some of these infant stars are growing planets which may already harbor life. Others are being destroyed, blowtorched and burned to death by a blistering flood of ultraviolet radiation from the region's brightest star. Thousands of stars were produced by a supernova and nebula in the area of Scorpio, which have now spread out across hundreds of light years, migrating across the constellations of Scorpius, Centaurus, and Crux in the southern skies. These are the survivors, formed from the remnants of an ancient parent star whose planets may have also harbored complex life. 5 billion years ago, a giant star, likely ringed with planets, some just like our own, exploded in a vast supernova, giving birth to dozens of new baby stars, including our own sun. When this ancient parent star exploded in a vast supernova, its closest planets were blasted apart into huge islands of mountainous debris and particles of dust, providing not just the seeds of life, actual living creatures and their DNA, but the water, rock, dust, and gases which gave rise to the Earth and our solar system. This debris included vast oceans and seas which were flash frozen into rivers of ice, some of which, millions of years later, would rain down and become part of the newly forming Earth and our solar system. And where there is water, there is life. Ancient meteors which have crashed to Earth are peppered with elements which are formed in the heart of this exploding star, including the decay product of iron-60 and a rare isotope sulfur-36, which is produced by the residue of supernova, and were found in meteorites that had circled the Sun for millions of years before crashing to Earth. Yet other meteors are peppered with grains produced by this titanic explosion. A detailed analysis of their isotopic composition indicates they are from an ancient star that long ago exploded in a supernova, shattering all the planets that made up its solar system. They contain not just grains, but fossils of microbial life. These fossils of microbes were all found deep inside carbonaceous chondrites, meteors from outside the solar system, which contain high concentrations of water. And where there is water, there is life. As our ancient parent star exploded in a vast supernova some 5 billion years ago, it created a huge molecular cloud which began to condense and form planetary nebula, also known as cometary knots. Because of gravitational pressures and cosmic shock waves, each of these planetary nebulae condensed and collapsed, forming hundreds of bright burning protostars surrounded by gas and oceans of mountainous debris. Thus, our Sun was born among a cluster of sister stars, some of which survived and are now likely circled by planets, just like our own. As the spinning molecular clouds of gas, hydrogen, dust, and massive debris collected and collapsed together, it began to rotate faster and faster, like a spinning ice skater pulling in her arms. Debris from the parent star and its shattered planets began colliding with other debris which collected together, becoming hotter and larger in size. An infant star was born, our Sun, a protostar still growing and not yet ringed with planets. Within a brief moment of time, ranging from 1 million to 50 million years, the pressures and density of hydrogen in the center of the protostar became great enough and temperatures hot enough that it triggered a thermonuclear reaction with the exploding, expanding thermal energy countering the gravitational forces of contraction, thereby creating equilibrium and a full-blown star, our Sun. Gas, dust, heavy metals, and giant masses of rocky debris continued to swirl around our newborn Sun, forming a protoplanetary disk which began to flatten out and clump together, the remnants of the dead parent star and its broken, shattered planets which gave birth to our own. A solar wind began to blow from the new burning Sun, dispersing the lighter gaseous elements to the far edges of the disk. Debris with the highest melting points, such as silicates and metals, formed the inner rims of the planetary disk and began congregating together to create the rocky, heavy metal interterrestrial planets, including the Earth. Thus, the Earth is comprised of the shattered remnants of the parent star and its rocky inner planets. By contrast, water, gases, and lighter elements and compounds were more resistant to the gravitational effects of our newborn Sun, but more susceptible to its heat and the solar wind which swept through the new solar system. Thus, these volatile icy compounds and incredibly toxic poisonous gases were blown away and remained at a greater distance from our Sun, eventually freezing and becoming part of the big gaseous planets, Jupiter and Saturn. Recent observations and computer simulations have demonstrated that planets can form in a relatively short space of time, from a few hundred years for a small rocky planet the size of Earth to 1 million years for Jupiter and Saturn-sized gas giants. According to the most conservative estimates, if mechanisms of accretion are very slow, it could take up to 1 million years for a massive solid planetary core to form. Then it would quickly snowball in size through clumping as debris continued to crash into it. 1 million years is more than enough time for any surviving life forms contained in the remnants of the exploding star and its shattered planets to find safe harbor within a planet made up of this debris. In fact, only one microbe had to survive, and once on Earth could cover the planet in bacterial offspring within a few months. Planetary debris, hundreds of miles in size, including a Mars-sized object over 4,000 miles wide, slammed into the growing Earth. However, so too did mountains of frozen water and oceans of ice, the remnants of ancient seas splashed into space when the parent star and its planets were destroyed. And where there is water, there is life, a single droplet containing millions of living organisms. Indeed, bedrock discovered in northern Quebec, which is over 4.2 billion years old, contains banded iron formations which were produced by living organisms. Thus, by 4.2 billion years ago, as life-containing debris from the parent star and its shattered planets continued to slam into the young Earth, the broiling Earth was cooling, becoming watery, and was already overrun by complex microbial life. What sort of creatures could survive such a cosmic disaster in a journey through space? Trillions, including what are called extremophiles. On Earth, all manner of creatures are able to live and thrive under almost every imaginable condition, from miles beneath the Earth, deep within oxygen-depleted iron cores, covered in salt, under extremely caustic alkaline conditions, in poisonous pools of boiling sulfur, and in acid lakes. Extremophiles can flourish even under the most extreme life-neutralizing conditions. Under sudden extreme changes of temperature, extremophiles instantly create heat shock proteins, cold shock proteins, or endospores which wrap around and protect them, enabling them to survive the infernos of hell or in freezing temperatures well below zero. Even under life-neutralizing conditions that threaten instant death, these creatures can instantly form spores or become dormant and exist in a state of suspended animation for hundreds of millions of years, only to reawaken and begin multiplying when they arrive in a life-sustaining environment. In 1972, a Russian scientist, Professor Shudinov, brought bacteria back to life which had been embedded for over 250 million years in crystals of potassium in the Ural Mountains of Russia. When they awoke from their long slumber, they began to reproduce. In the year 2000, Professor Vreeland reported a similar discovery. He brought microbes back to life that had been embedded in salt crystals buried 569 meters beneath the Earth and dating back 250 million years. These bacteria, B. permians, survived by creating spores. Some of these bacteria began multiplying once they were brought back to life. If the Earth were shattered and destroyed, trillions of these creatures would easily survive buried within tons of debris and oceans of water, some becoming dormant only to reawaken after landing upon a suitable planet. Although the new Earth was alternately freezing and broiling, it had quickly become habitable to creatures already adapted to these conditions, particularly as highly toxic poisonous gases were being blown away and swept into space by powerful solar winds emanating from the newborn sun. The solar wind is radiated by the sun as a continuous stream of charged particles, of plasma, creating a tenuous atmosphere that spreads out and permeates the solar system. Because water, oxygen, and the lighter gases were blown away by the solar wind of the new sun, thus becoming part of the outer planets, and as the solar wind and the melting Earth blew away all oxygen and water molecules and whatever the Earth had for an atmosphere, all the essential ingredients for the creation of an organic soup were absent. In fact, any organic molecules on the exposed surface of the planet would have been instantly destroyed by ultraviolet and cosmic rays, as there was no atmosphere, no oxygen, and no layer of ozone to protect them. The new Earth was a toxic, poisonous planet, capable of sustaining only fully formed and complex life forms already adapted to living in these conditions. Even if the essential ingredients had been present, any DNA or RNA molecules or their bases and nucleotides would have instantly suffered profound photochemical damage and would have been destroyed if exposed to as little as 20 nanoseconds of ultraviolet light. And yet, by 4.2 billion years ago, 300 million years after the formation of the Earth, and certainly by 3.8 billion years ago, our planet was already contaminated with life, even though all the essential ingredients for creating an organic soup were absent, and the lack of ozone or an atmosphere would have meant instant ultraviolet death for naked DNA, its nucleotides or bases. Which means these molecules of life could never have been randomly assembled on this planet. Even fragments of DNA or RNA would have been instantly destroyed by UV rays. Thus, life could never have begun on Earth in an organic soup. Only complex living creatures, whose DNA was protected inside a biological living membrane and who had arrived buried deep within debris, could have survived the conditions which characterized this planet for the first billion years after it was formed. Because highly toxic poisonous gases were swept into space by the powerful solar wind, which simultaneously formed a protective plasma bubble of charged particles, those creatures who had been cast to Earth were able to emerge, multiply, and begin genetically engineering the planet in preparation for those yet to be born. Those microbes which unwillingly hitchhiked to the new Earth immediately began digesting the planet and excreting gases, oxygen, and magnetite as waste products. As all poisonous and other gases had been swept away by the solar wind, the Earth's new atmosphere would be produced biologically. Icy comets would provide the Earth with oceans of water. The replacement atmosphere came from three sources: gases released from within the Earth, iron-eating and mineral-eating microbes releasing various gases, including oxygen as a waste product, and icy comets and oceans of frozen water striking the Earth, the watery remnants of ancient worlds destroyed. In fact, even as the Earth was still forming, bacteria had already taken root and were flourishing, multiplying, and genetically altering the Earth, preparing the planet for the metamorphosis and replication of living creatures who long ago lived on other worlds. The first steps involved altering the soil and creating an atmosphere. Bacteria engaged in photosynthesis and released oxygen and other gases as a waste product, thereby providing the Earth with an oxygen atmosphere, altering the climate and preparing the planet for the metamorphosis of oxygen-breathing creatures. Yet others liberated phosphates, sugars, nitrogens, and ammonia from the soil, playing a major role in the carbon cycle, preparing the land for plants and complex soil-dwelling animals. Thus we see that the first creatures on Earth engaged in photosynthesis and began releasing as a waste product free oxygen, which was pumped into the oceans and the atmosphere. This eventually led to the creation of ozone, which blocked out life-neutralizing ultraviolet radiation. This allowed complex creatures to emerge from the sea and crawl upon the Earth. Thus, the basic chemistry of the Earth's surface, oceans, and atmosphere were determined by biological activity, especially that of the many trillions of microbes who dwell in soil and water. Once the environment had been significantly altered through biological activity, and as the environment interacts with regulatory DNA to activate or inhibit various genes, new species began to emerge, perfectly adapted for an environment which had been prepared for them. Of all the planets in our solar system, only the Earth was ideally suited for genetic engineering and maintaining a developing atmosphere capable of sustaining increasingly complex life. This was made possible in part by the Earth's magnetic field, which extends tens of thousands of miles into space, forming a protective magnetosphere. The Earth's magnetic field is produced by electric currents generated by the planet's liquid metal core, and supplemented by mountains of magnetite secreted by iron and other mineral-eating microbes. As the magnetosphere grew in size, it began to deflect the sun's powerful solar winds. By contrast, Mars has a very weak magnetic field, and the solar wind causes the Martian atmospheres to continually bleed away into space. The Earth's magnetic field was able to protect its newly developing atmosphere from the solar winds, keeping it bound to Earth. Simultaneously, the solar wind, comprised of plasma particles, created a protective plasma bubble, the heliosphere, which shielded our planet and the solar system from deadly, life-neutralizing cosmic rays. Because of the solar wind and the Earth's magnetic field, the surviving microbes contained in the planetary debris which formed the Earth were able to go forth and multiply. Thus our solar system is a child of an ancient exploding star which had been likely ringed with planets crawling with all manner of life, the remnants of which form the Earth, our Sun, and the planets of our solar system. Naturally, any survivors of this cosmic calamity, those buried within mountains of debris, would have also become part of these newly forming planets. Only the hardiest of creatures, and those already adapted to feasting on silicates and metals in the absence of oxygen or an atmosphere, would have found the newborn Earth to be a habitable planet. On the modern Earth, 1 trillion microbes in their DNA flourish and multiply under exactly these conditions. Our ancient ancestors journeyed here from the stars. Only life gives rise to life, and life may be an intrinsic feature of the living, infinite universe.